Welcome to Physics 142. I'd like to work out one of the homework problems. It's not one of the ones you have to turn in, but it's similar to others that you have to turn in. And so what we'd like to do is find the electric field due to a dipole at a point on the axis of the dipole. And so here is the information that's provided in the homework problem. It says that there's a dipole composed of two charges lying on the y-axis, right? And here's the x-axis. Here's the y-axis. One charge is at 0 plus 6a. The other charge is at 0 minus 2a. And they're equal and opposite charges, plus 3q minus 3q. We want to find the electric field at the point 0, 10a due to this dipole. And so at this point up here, we're going to have contributions due to the positive charge. And following the textbook, we'll call that E plus. We'll also have a contribution due to the negative charge. We'll call that E minus. And all we have to do is write down expressions for those two contributions and then add them up, taking into account the fact that they point in different directions. So E, remember, for a point charge, we'll write this down because it's the starting point for everything that we do when we're dealing with point charges. For a point charge, E, the magnitude of E is given by k times the point charge over the distance squared. That's the electric field at a point, a distance r away from the point charge. So the point that we're interested in is up here at 10a. Well, one distance that we have to figure out is the distance between it and the positive point charge, and that's easy to see that that's just 4a. And then we also need the distance between that point and the point charge that lies below the x-axis. And it's pretty obvious to see that 10a minus a negative 2 is equal to a plus 12a. So those are the two distances that are going to go into the denominator in the expression we'll write down for the electric field. So E total, and I'll drop the total in a minute, but just to remind you how this works, E total is equal to, as a vector, E plus the electric field due to the positive charge, and that will have a positive y component, plus the vector E minus, which actually has a negative y component. So from here on in, what I'll do is write down the expressions for the magnitudes of those two, and then put in a minus sign for the E minus, because it's pointing downward. Alright, so k, this will be for E plus now. We'll write them down as two separate terms. K times 3q over the distance squared, and the distance is 4a. Quantity squared, remember you got to square the 4 as well, minus k times 3q over the distance squared, but now we have 12a. Quantity squared, and because I put the minus sign in front of the second term, I can already say that this is simply in the j hat direction. The first term is the positive contribution, that's the E plus vector. The second term is the negative contribution, that's the E minus vector. And from here on in, it's really just a matter of doing some simple arithmetic, because we see there's a 3kq factor that we can pull outside, and there's also a 4a squared that we can pull outside in the denominator. And so we can write this as 3kq over 4a quantity squared, and that means that the first term, once we factor that out, will just be 1. The second term is going to be 1 over something. Now what's the difference between those two? The difference is a factor of 3, but it's a factor of 3 inside a squared term. Alright, so we write it like this. And if you're not quite sure if that looks right, you can multiply it out and check to see that what we get here, if you multiply the term pulled out in front by the term in the denominator, we get 16 times 9, or 144, right, which is the same as 12 squared. So this works out right. The term in the brackets now then is just 8/9, so this becomes 3kq over 4a quantity squared times 1 minus 1/9 or 8/9 times j. And now there's going to be a little simplification that goes on here because we've got a 16 here. Well, the 3 and the 9, the 3 cancels, so that leaves us with 8kq over 16a squared times 3, right? There's basically a 3 down here left over when the 3 and the 9, we canceled out a common factor of 3. Here then the 8 over 16 is just a factor of 1/2. So the 2 and the 3 multiply to give a 6. So the final answer is kq over 6a squared j hat for the electric field due to this dipole at a point on the axis of the dipole. Pretty simple calculation. Let's look at the answer to see if it makes sense. The sign certainly makes sense because it's in the positive j hat direction, right? So plus j hat, that checks out, the sign checks out. And again, the units check out because the units of E are equal to whatever the units of the Coulomb constant are times the units of the charge divided by the units of a distance squared. And that, from our very first expression for the electric field of a point charge, is always correct. The Coulomb constant times a charge over a distance squared is always the correct units or dimensions for an electric field. So that's how to do simple calculations of the electric field produced by dipole. You just treat the two individual charges like point charges, add them up, and you're all set.